So I thought we'd just look at a couple of the more interesting induction problems that have appeared over the past few years. So in 2006, it started off with this. In itself, people looked at this question and went, probably choked a bit, like that. What are we going to do here? Although they gave us a bit of a hint, we're going to use our difference of two angles there formula with tan to show this lovely expression of 1 plus tan n theta plus tan n plus 1 theta is equal to the cotan. Oh, hang on, where'd cotan come from? And then tan n plus 1 and tan n. So I guess when I first looked at this one, I thought, well, how in the heck am I going to use that formula to get this result? I guess I'm looking for two angles. Which one's going to be alpha, which one's going to be beta. And if I look in the question, I've got n theta, n plus 1 theta, but I've also got theta. So that's when I said, all right, what I'll do is I'll use alpha to be n plus 1 theta, beta to be n theta, because remember we're talking about the difference of two angles, and so the difference between n plus 1 theta and n theta would create the theta that I'm looking for. So I've got all the angles we want. So I've substituted in n plus 1 theta and n theta into the formula. Now we need to get to this next step. Now, I don't know what you're seeing when you look at that, but I'm noticing that the left-hand side here is the denominator on the right-hand side. Okay. So if I was to multiply by the denominator on the left-hand side, it does give me the left-hand side of what we're trying to prove, but I've got this pesky tan theta now. So if I divide by tan theta, now we can see why they've put cot there, because the reciprocal of tan is cotan. So we actually do have the result. It's just that we've got it over tan theta, but the reciprocal of tan is cotan. We've got our result. So that was the first part of this question. When you look at the, it's not called Border Studies anymore, the NESA website, they put up examiners' comments with HSCs to give you a bit of an idea of what people did well, what they didn't do so well. So the comment on this one was, the first part, that was not done well. Right. Presenting circular arguments, and that means those are the ones where you end up coming back around and you get some sort of statement like 0 equals 0. Oh, you beauty. So a lot of people just didn't know how to handle that, because it is, if we just look at it again, they say it looks horrendous when you're like, what on earth am I going to do? But as I say, if you think through the problem like I did there, was, well, they've given me a formula I've got to use. What is in the answer? Let's substitute things in, and it actually only takes a couple of steps if you persevere with it. But as I say, they said that the first part was not done that well, but it's all right. The first part, I guess, was a hint, if you like, because you're going to use that formula to help you do the problem later on. So that was the point of part one. However, there were a number who successfully did it, and easily saw the substitution. So I guess they're saying there are two sets: those that had no idea and those that bang got it straight away. Oh yeah, that's how we're going to do it. It was only worth 1 mark, by the way. So a lot of people spend a lot of time, and sometimes, especially in the extension exams, you got to weigh up how much time am I spending on this question. Is it worth this 1 mark? I can always come back to it. Maybe I'm better off working through the rest of the paper, and I'll come back to the 1 mark with a fresh mind, and maybe it'll come in. So that brings us to the induction problem. So it's a series type. We're going to prove tan theta, tan 2 theta, tan 2 theta, tan 3 theta, and so on and so on and so on is equal to that expression on the right-hand side there. Right? Series type. Well, we know how to handle that. We'll prove it true for the first case. Now, I've actually done the right-hand side first of all. So if I sub in n equals 1, I'll get negative 2 plus cot theta tan 2 theta. On the left-hand side, when I substitute in, I get tan theta tan 2 theta. I've got to show that these are the same. Okay. On the left-hand side, I've added 1 and subtracted 1. Reason I've done that is I've said to myself, well, what was the point of part I in this question? Why did they ask me to prove this result? And if you look on the left-hand side, if you look on the left-hand side of the result, it's 1 plus tan. I only had tan. So that's why on the left-hand side I added 1. So I've got that 1 plus tan, which will allow me to use the formula they just asked us to prove. But then obviously I can't just change the question, so I've subtracted 1 as well. So 1 plus tan, using the formula that they just gave us, is cot theta, tan 2 theta, minus tan theta. Expand out the parentheses, and I get the cot theta, tan 2 theta. Cot times tan, they're reciprocals, so that's just going to become 1, and there's the negative 2 we're looking for, negative 1, negative 1. So it does come out. So yes, it is true for n equals 1. That was just step 1 of this induction that year. So you imagine what people are thinking in this particular exam. Oh my God, that's meant to be the easy part. That's meant to be the gift, you know. Substitute in n equals 1 and we get the answer. What's going on? So now I can do my assumption. So for n equals k, we want to prove for k plus 1. So everywhere I see an n, I'm going to replace it with a k plus 1. There's the beautiful expression we're going to try and prove. Our right hand side becomes minus k plus 2 plus cot theta, the tan of k plus 2 theta. Well, let's do our proof. It's a series type, so I'll set it up. So I'll rewrite it as the sum to k plus the k plus 1th term. And we've done an assumption for the sum to k. So we'll sub in that assumption. So it's still the same idea that we've been doing. It's just a little bit more of a horrendous looking terms that we're playing with. So what have we now got? Minus k plus 1, cot theta tan k plus 1 theta, tan k plus 1 theta, tan k plus 2 theta. We want to get to minus k plus 2. I've got minus k plus 1 plus cot theta tan k plus 2 theta. Ooh, okay. Well, there's that tan again. Maybe I use that formula. So let's do that. But of course, remember, to use that formula, I had to go 1 and then subtract 1. Well, I did that all in one step, you'll notice. I've subbed in the formula, and there's the minus 1. If you wanted, I suppose, you could write the line in to make it more obvious and go, oh, I'm going to rewrite this as minus k plus 1 plus cot theta tan k plus 1 theta plus 1 plus tan k plus 1 theta tan k plus 2 theta minus 1. So the same as I did in step 1 where I added 1, subtracted 1. But then I could use that formula that we've proved and we end up with the cot theta part. All right, so again, let's have a look at where we're heading to. I want to get minus cot. Oh, good, I've got the minus k plus 2. Because look, I've got the minus k plus 1 over here, and at the end I've got minus 1. Put those together, we've got the minus k plus 2. I want cot theta tan k plus 2 theta, which I have got when I expand that out. So it looks like, let's just do a bit of work here. We've changed the minus k plus 2, expand out, yes, look what happens. I end up with minus cot theta tan k plus 1, which cancels with the plus cot theta tan k plus 1. Bang, there's our result. It drops out. So yep, all good. Works for k plus 1 if it's true for k. And since the result's true, etc., etc., etc. One of the more interesting induction problems, as I say, that has appeared. What did the examiners say? Part 2, most candidates attempted this part. However, many only earned the mark for stating the inductive step. Right. When we're marking HSCs, there's a marking scheme we work with, but you then go through several papers to see whether the marking scheme works. And if you get one which turns out to be a more difficult question, which clearly this one did that particular year, what happens is you go, ooh, hang on, maybe we need to change this marking scheme. And there's when you're marking a 3-mark or more question in the HSC, when it comes to marking, we always say, look, the first mark should be easy to get. You'd be surprised sometimes what we end up giving 1 mark for. So for this one, normally in an induction you'd say, I will give him 1 mark for testing n equals 1. But you saw that was difficult this time. So they probably had to adjust it and say, look, I'll tell you what, we'll give them 1 mark if we see or they state the inductive step. The inductive step, I guess, is showing that you're substituting the assumption so we know it's true for k plus 1 if it's true for k. That sort of thing. So they're looking for, do they actually understand what induction is? The proof might have been a whole heap of garbage. But if in it they could see, yeah, at least they understand what induction is, we'll give them a mark. Now, that's not to say they'll do that every time. It's the level of difficulty of the question sort of determines where that easy mark's going to come in. They could not prove the expression true for n equals 1, as they were not able to use part I. That's what I'm saying. You've got to think, hang on, I've got this induction question here. Why on earth did they ask me part I? Clearly, this is going to help me somehow in solving it. And consequently, they then couldn't do the inductive step, because you'll notice I used it again in that induction. Here's one that was a little bit different. It's still a series type, but instead of adding terms together, we're multiplying terms together. But we can still use the same idea. So the first case for this one, oh look, I did find the greater than or equal to symbol, is greater than or equal to 3. So left hand side would be 1 minus 2/3, which is 1/3. Right hand side, yep, that also becomes 1/3. So all good for n equals 3. My assumption therefore will be those multiplied together. We want to prove, and I'll multiply in the next term rather than add in the next term, 1 minus 2 on k plus 1. So I will set it up like a series type, but instead of adding, we're now multiplying. So it's, I guess we don't call it the sum to k, the multiplication to k, or whatever we call it, times the k plus 1th term. So those first k terms multiplied together, we have assumed that's 2 on k minus 1. Righto, we're trying to end up with an algebraic fraction, 2 on k plus 1. Let's turn this second one all into one fraction. Now the top of that becomes k plus 1 minus 2, which is k minus 1. And that drops out quite nicely. The k minus 1 cancels with the k minus 1. We get 2 on k plus 1. So having shown you that first example of an HSC question, I don't want you to think that every HSC induction question is like this incredibly difficult question. That one's not too bad. A little bit different because it's not addition, it's multiplication. Where that would catch people out are those people who just learn a technique and go, oh, well, it's sum to k plus term k plus 1, and they still want to use addition or something rather than using the idea of induction. So, okay, all good. Works for k plus 1 if it's also true for k, hence true, etc., etc., etc. So, many submitted excellent responses, all necessary components of the induction proof. Weaker response, yes, didn't verify for n equals 3. Force of habit, people would have tried n equals 1 for the first case. Had incorrect statement of the assumption or incorrect use of the assumption. Algebra skills, obviously, if you didn't have good algebra skills, that one would have been tricky because you had to play with the algebraic fractions. And that's what I was just talking about, rote learning of that idea of sum to the k plus term k plus 1. It's an idea that works, but it only works when we're talking about those series questions where we're adding terms. Okay.